Just I'll read the question again. Chef bakes cake 3. Chef is an expert baker. Each cake costs him 30 coins to make and then he sells for 50 coins. Chef is going to sell cakes for n days numbered 1 to n. On ith day, AI customer will visit the chef's shop each and buy exactly 1 cake each. However, chef preferring uniformity will always produce the same number of cakes at the start of every day, say X, because cakes become stale fast. He cannot keep the current day's cake for the next day, and you want to decide this non-negative integer X in such a way that it maximizes chef's profit over all n days. So the first line of input will contain a single integer t denoting the number of test cases, then n and the array a. So basically the constraints are t is 100, n is 100 and ai is also 100. So maximum n cube can pass since there is no constraint over sum of n overall test cases. So the complexity would be t into n cube. That would be 10 to the power 8. So maximum n cube can pass. Let's just explain the question to you guys. Basically what happens, we are a shop owner and every day A1 problem A. So we are a shop owner and every day A1, A2 and AN customers come to our shop and we have X cakes. For each day we have X cakes. And each customer will buy a maximum of 1 cake. So basically, if X is less than A1, then first X customers will buy a cake and then the rest of the customers will not get a cake since we only had X cakes. And making cost of the cake is 30 and selling price is 50. So let's see the test cases. First test case is 3111. So basically we can choose X as 1 since then each customer will buy a cake on every day and that will maximize our profit. So the profit we'll get is each day will spend 30 coins in making. So minus 30 and 50 coins will get after selling. So each day we'll get 20 coins and on 3 days we'll get 60 coins. So 60 would be the answer of the first case. Then 221. Here we can either choose X as 1. Then what will happen is first day we'll get a profit of 20 since only one customer will get a cake. Second cake we cannot sell as we only made 1 cake. And then again second day we'll get a profit of 20 and on the third day we'll again get a profit of 20. So 60 if we take X as 1 and if we take X as 2, what will happen? First day we'll get a profit of 40 since 2 cakes are being sold. So minus 60 would be the making cost and plus 100 would be the selling cost. That way 40 profit. Second day again 40 profit. And then third day minus 60 and plus 50. Basically we'll have a loss of 10. Since we made 2 cakes, so we had to spend 60 coins and we only sold 1. So we lost 10 coins overall. So this way overall profit would be 70 and this would be better. So 70 would be the answer in this case. So one observation we can make from here is that whatever X we take, we are sure that X would be less than equal to maximum of A1, A2 and AN. Because if we take X any bigger than this value, then we are just wasting cakes. Since the maximum we can sell in a day would be this, and if we make any more than that, then we would just waste. So X would be less than equal to maximum of this. This is the observation that we can use to solve because the constraints allow us to brute force it. Since AI is less than equal to 100, so X would also be less than equal to 100. So we can check for all X. For X equal to 1 to X equal to 100, we can check. And how do we check what's the profit for each X? Once we calculate the profit for each X, we can check the maximum profit and that would be the answer. So the profit for each X can be calculated like this. Basically, each day from 0 to n minus 1, what we sell the minimum of X comma AI cakes. Basically, we sell these, so 50 into this and minus 30 into X. This would be the daily profit. And we can just sum this to get the profit for a certain X. I'll explain what this line means. Basically, this is working because if let's say X was less than AI, then what will happen? X customers will get cake, and after that, no one will get cake because our cakes are over. So in this case, we sell X cakes, and if X is greater than AI, in this case, we sell AI cakes. So basically, whichever was lower, we sell that. We sell those many. If X was lesser than AI, then we can sell X cakes. If AI was lesser than X, then we sell AI cakes. So we sell minimum of X and AI cakes, and we sell at a price of 50, and we need 30 to make it. So minus 30X and plus 50 into the number of cakes that we sell on each day, summed for all the days. That would give the total profit for a given X. And we can just maximize this for all X. And that would be answer. So what the time complexity of this would be, since we are checking for all X 1 to 100, that would be 100. And we are checking each in O of n. So that would be another 100. So O of 10 to the power 4, that will easily pass. So I'll show you guys code. Basically, we take the vector input and we check for all X 1 to 100, and current would be the current profit for this certain X. It would be for each day, we calculate each day's profit. It would be the number of cakes we sold into 50 minus 30 into X. So, and answer would be maximum of answer and current. Answer was initially 0. That would be the case when we don't bake any cakes, where X is equal to 0. So answer can never be less than 0. And we just do answer maximum of curve and see out answer. That was a fairly simple question. Do you guys have any doubts in that? Okay. Let's move on to the next question. Second question was mark all. You have n numbers 1 to n initially, all of them are unmarked, and you want to mark all of them by the end. There are n possible operations numbered 1 to n, where the ith operation costs AI coins, and you can use it in exactly one of the following ways. Prefix type, mark all the numbers in the range 1 to I, and suffix type, mark all the numbers in the range I to n. Each operation can be used at most once. Find the minimum cost to mark all the numbers 1 to n. We have for each test case an n and the integer array a. The constraints are n is less than equal to 2e5, and sum of n over all the test cases do not exceed 2e5. So the expected time complexity would be O of n, since n is O of n or O of n log n. Let's see the test cases. Problem B. Basically, what the problem is saying that we have an array of 1, 2, 3, 4 till n indices, and initially all of them are unmarked. Initially unmarked. What we can do is perform this operation. So what is this operation? We choose an I, and for this I, we either mark all the indexes in 1 to I or all the indexes in I to N. So for an I, we must do one of these operations, and we cannot do for the same I. Basically, each operation can be used at most once. So if we use the operation I once, we cannot do it again. So we choose an I like this, and we need to mark all the nodes and minimize the cost. Basically, each operation I has cost AI, and we need to use these operations to mark all the nodes in such a way that the cost is minimized. Let's see the test cases. Test case 1 is 2, 1. Test case 1 is 2, 1. So basically, okay. So what we can do is A1 is 2 and A2 is 1. So A1 is 2 and A2 is 1. And we have an array of 2 elements, n equals to 2. We have, for this, we can either do 1 to 1, or we can either mark 1 to 2. This would be the prefix operation, this would be the suffix operation. For this, we can either mark 1 to 2, or we can either mark 2 to 2. This would be the prefix operation, and this would be the suffix operation. So we can clearly see that using this operation, we can mark all of the array at once. So we know that there is a way to mark the array in cost of 2. And again, similarly, from here we know that we can mark the array in cost of 1, since 1, 2 is the whole array. So we have 2 and then we have 1. And using any more operation than these would be just inoptimal, because even if we use this operation, we would still have to use this. So then we would get cost of 2 plus 1. So that is not. So 1 would be the answer for this test case. 1. That one observation made in this test case was basically for the A1 and AN operations. What we can do is, for this, we can take the 1 to N, that is the suffix operation. And for this, we can take again 1 to N prefix operation. And this will mark the whole array in just one operation. So I can use either of these to mark the operation. The optimal answer might be something else, but these two can be the optimal answer, could be. So answer would be less than equal to minimum of A1 and AN. That is one thing. We saw it here. The next test case is 314. So I have 3 elements, 1, 2, 3. If I use this operation, I can mark the whole array in 3, or I can just mark this in 3. So if I use this operation, I would certainly be just marking the whole array, because otherwise then I'll have to use more operations to mark the full array, and that would lead to more cost. So if I use this operation, I'll just mark the whole array. If I'm using this operation, then I can either mark this or I can either mark this. That if I mark this in one cost, I would need to mark this, and for this I'll need to either use this or this, which would again lead in the cost being 5 or 4. So again, using this would not be good. And I can again use this, and in just one operation, I can again mark the whole array in the prefix operation. So 3 or 4, and the answer would be 3. So let's see. Another observation that I made was that I would never have to use the prefix operation twice. Because let's say I have an array 1, 2, 3 till n. If I used prefix of, if let's say if I used two prefix operations 0, 1 to ai and 1 to aj, and let's say aj was greater than ai. So this operation would be just a waste. Using this operation would be a waste because when I do use this operation, all 1 to ai get marked, and when I do this operation, all 1 to aj get marked. So basically, if I'm doing this operation, then doing this operation would be a waste. So therefore, we can prove from this that at max, only one prefix operation is made. And similarly, we can see for suffix also. Let's say we mark ai to n as 1 as marked and aj to n as marked in two different operations. Then if aj was less than ai, let's suppose, then using this operation was a waste, since we already marked all the nodes that we had in this operation in this operation. So using this operation would be just better than using this operation, and this operation was a waste. So again, from this we proved that at max only one suffix operation. So now let's try to find the answer using these two observations. So basically, let's just say that I used the prefix operation 1 to i. 1 to i. So let's just say that I use this prefix operation. Just let's say that 1 to I was the optimal prefix operation. So now I'll have to make one suffix operation to mark the entire array, because using two suffix operation was inoptimal. We proved that. So I'll need to use at max one suffix operation. So what we can do, we need to find a j somewhere here such that j is less than I, less than or equal to, no, not equal to, because we cannot perform the same operation twice. So if we already performed the prefix operation with I, we cannot perform the suffix operation with I. So for j less than equal to I, we can select any j. Let's say, for example, here. And if we perform the suffix operation, then this much array would be marked. And since we already had marked this array, and in the next operation we mark this array, then the whole array would be marked. So we can select any j less than I, or what we could have done is select j as I plus 1. Even then all of the array would be marked, because we had already marked this much, and then in the next we would mark this much. In the first operation we marked 1 to I, and in the next operation we marked I plus 1 to n. So that marks the whole array. So either we take j less than I, or we take j equal to I plus 1. Suffix operation. So this for a prefix operation at I. Now, since we need to minimize the cost, what could be the minimum cost? If I'm performing the prefix at I, that would take me AI of cost. And then I need to perform another suffix operation for j, where j would be less than I or j is I plus 1. So minimum of A1, A2 till AI minus 1 and then AI plus 1. AI plus 1. So this would be the suffix operation. Since I could have chosen any one of these to mark the whole array, I would choose the one with the minimum cost to minimize the overall cost. So the total cost would be AI, which is the prefix operation, plus the minimum of these plus the suffix operation. Now to find the answer, what we can do is basically check for every AI. Check for every I. 0 to n. Also, actually not 0 to n, 1, sorry, we are using 1 base now, so 2 to n minus 1. Basically 2 to n minus 1, because we made this observation above that if I'm using A1, we can already mark the full array. And if I'm using AN, we can already mark the full array. So we don't need additional operations with these. If we are using these, we don't need additional operations. So basically we leave these out and just initialize the answer with minimum of A1 and AN. And then we can check for every I, this cost function, basically AI plus minimum of A1, A2, AI minus 1, comma AI plus 1. So if we calculate the minimum value naively, that would take O of n, and the overall complexity would become O of n square, which will not pass in this case. So we can optimize this. We can pre-calculate this and just find an O of 1. So we can just either we can pre-calculate a minimum array where the array of I would be just minimum of array of I minus 1 and A of I. Either we can just calculate this and then this whole thing can be replaced with just ARR of I minus 1. Then we don't need a loop to calculate this anymore, and this would be just O of 1. Or one other thing we can do is we can basically maintain a variable, let's say some value, which every time we iterate, we just, after we calculate this, we just update value with minimum of value and AI. So basically in the next iteration, automatically we can just replace this with value, since it already had minimum. So yeah, these are like these two approaches are very much same. Here we just pre-calculate the minimum array, and here we just calculate it on the go. So we can then solve this question in O of n. I'll show you guys the code now. So this is the code. We just input the array, and answer is initialized as minimum of v0 and vn minus 1. And initially the value val is this variable, basically, which holds minimum up to I minus 1. So we are starting the loop from 1. So we can put val as v of 0 because we need to till I minus 1. And we can calculate answer as minimum of answer comma answer and val comma vi plus 1. This thing and this thing. That would be, and vi is the prefix sum cost, this. Now we update the value as minimum of value comma vi, so that the next iteration we can use this. So that was it, and then we see out the answer. Did you guys understand the solution? Is this correct approach for this question, that if we take prefix min for all indices and same for suffix, and then compare if prefix is more closer to n or suffix is more closer to index 0, then we can add the both indices value and that's the answer. Uh, can we I did not understand what you are trying to say in this approach. Correct for this question. We take prefix min for all indices. You're talking about question B, right? Yes. Okay. So if we take prefix min, if we take prefix min for all indices and same for suffix, and then compare if prefix is more closer to n, prefix is more closer to n. What does that mean? Like we maintain prefix min array and suffix min array. Yes, you can maintain prefix min array and suffix min array and use that to solve. Basically, but still, I mean, like what, do you want me to unmute you?
Hello.
Yes.
Yes, so my approach is like to have a prefix min array where we, for every indices, we compute the minimum indexes, minimum of the current or the previous indexes for every indexes, and same for the suffix. Like
In
prefix min
suffix, we store the minimum of current and all
previous,
the previous or after.
in suffix after.
Okay, okay.
And for suffix array, we will do the same for the from ending to the start of the array.
Okay.
And then after computing these two, we will find indexes which is like minimum, and the prefix array indices crosses that, and suffix is also crosses that, means prefix indices array is closer to n and suffix will be closer to 0.
I didn't understand this last step. Closer to n, what do you mean by that?
Like we have to change for the prefix, we have to change the mark the array from 1 to n. So I'm saying that
Yes. Okay.
uh, that it will be marked from 1 to, let's say, I index which is greater than I by 2, and matlab n by 2, and for the suffix array we will target such a index which is smaller than n by 2. That's how we
Okay, okay,
compute the
okay.
array.
Okay, yes, yes, yes. Basically, so what you are saying is you'll take an index I and then mark the prefix from 1 to I, and then now you need to have a suffix that is that starts before I.
Yeah, that's it. That is smaller to I, means 0 to I minus 1. From there, we will take the minimum of suffix and add those two indices. That's our answer.
Yeah. You can do this. This would give the right answer. Basically, this is what I did. I just didn't calculate the prefix min array.
Okay.
Okay. Okay, so I think it is clear to everyone now. Let's move on to the next question. So, Munchys Modulo, you are given an array A of n integers. Find the maximum value of AI mod AJ plus AK. Overall possible triplets satisfying I, J, K less than equal to n, and I, J, K are pairwise distinct. So n is less than equal to 5000 and AI is less than equal to 10 to the power 9. Sum of n square does not exceed 5000 square. So expected time complexity would be n square, since n square is less than 1 to the power 110 to the power 8, so n square can pass. Let's see, basically, I just problem C. So we need to maximize the value of AI modulo AJ plus AK, where I, comma J, comma K are distinct. That's it for the question. Let's see the test cases. 1, 2, 3 and 1, 3, 3. 1, 2, 3. So let's try to brute force our answer for this test case. One thing we can do is 1 modulo 2 plus 3, which is 1 only. And then 2 modulo 1 plus 3, which is 2 only. And 3 modulo 1 plus 2, which will be 0. Because 3 mod 3 would be 0. Mod is remainder. So this, and since we need to maximize this, our answer would be 2. Answer is 2. And the next case, it is 1, 3, 3. 1 mod 3 plus 3 might be the answer, or 3 mod 1 plus 3. Or again 3 mod 1 plus 3, which is same. So this would give us 1 and this would give us 3 mod 4, which is 3. So again the answer would be 3. So what I observed from these, this is like basically AI mod AJ plus AK can, first of all, it will always be less than AI. First of all, this, because remainder can never be more than AI. Since if I'm divide, if AI was, so basically if AJ and AK are greater than AI, then the remainder would be just AI. And if AJ, sorry, not equal to, sorry, if AJ plus AK is greater than AI, then the remainder would be just AI. AI modulo AJ plus AK would be simply AI. But if AJ plus AK are less than equal to AI, then the modulo AI AJ plus AK will have to be less than equal to AJ plus AK. Less than AJ plus equal, not even equal to. Less than AJ plus AK, which is less than equal to AI. So basically our modulo in all cases would be less than equal to AI. We can understand this more if we take some examples. What happens, let's say if we take the remainder 10% 7, we would get 3. Since we what we are doing here is basically splitting it like this: n equal to 7 into some quotient q plus r. So this r can never be more than 7. R has to be less than 7, because if r is more than 7, what I can do is basically make it of this form: q plus 1 and then r minus 7. So r can never be more than 7. It can also not be equal to 7. It has to be less than 7. Remainder has to be less than the modulo mod. So if I'm taking mod 7, then the remainder must be less than 7. And what happens if I take 10 remainder 13? Then I would simply get 10 as the remainder. So this was this property. If AJ plus AK is greater than AI, basically 13 was greater than 10, then the modulo would simply be AI. But if AJ plus AK is less than equal to AI, then we would get some modulo which would be less than AJ plus AK. Since remainder is always less than the mod. And since we already took this as less than AI, so it would be less than equal to AI. So this thing is always less than equal to AI. This is one observation. And it is maximum when, let me write this again, AI modulo AJ plus AK is always less than or equal to AI maximum when AJ plus AK is greater than AI. So we need to find the maximum answer, right? So for an AI, we should choose AJ and AK such that AJ plus AK is greater than AI. Then the answer would be maximized, because for this function is always less than equal to AI and it is equal to AI when AJ plus AK is greater than AI. So obviously, if we need to make AJ plus AK greater than AI, then we can simply choose AJ and AK as the largest and second largest number. What we'll get by doing so is basically now for if for all AI except AJ and AK, basically since we need to be pairwise distinct, we need to keep IJK as distinct. So for all AI except the largest and second largest number, we would know that AJ plus AK is always greater than AI. Since these are the largest and second largest number, and this would be some smaller number than these. This would be smaller than these. So we know that AJ plus AK would be always greater than AI. So if we have a sorted array, then in that AI modulo AN plus AN minus 1. Basically in the sorted array, I am assuming that the last two elements would be the largest. So this would just give us AI for I equal to 1 to n minus 2, since we need pairwise distinct. So for our answer, we already know that answer would be, if we choose as AI as anywhere from I to n minus 2, we would just get our answer as maximum of A1, A2 till A n minus 2. Now what happens if I choose AI as A n minus 1? Now I won't be able to keep the second largest element here, since all these three need to be distinct. But still, since we know that we know that AN would be greater than equal to AN minus 1, since it was a sorted array. So AN would have been greater than equal to AN minus 1. So AN minus 1 modulo AN plus A1, let's say. Now this term again will be bigger than this term. So this will again give us the answer AN minus 1. Since we in the constraints we see that AI is always greater than 1. So this term would always be greater than AN, which is greater than equal to AN minus 1. So this term would always be greater than AN minus 1. And since it is greater than AN minus 1, we'll get this as the remainder. So we add another element here. So our answer will be now maximum of A1, A2, AN minus 1. Now what happens if we choose AN as the ith element? So then it would become AN percentage AI plus AJ. Now I and J can be anything, and I cannot guarantee that AI plus AJ is greater than AN. We cannot guarantee this, since AN is the maximum element. We can see this in a simple test case, for example, 2, 3, 7 maybe. Now 7 is the maximum element, and we cannot guarantee any two elements that gave us some greater than 7. So this property cannot be guaranteed for the largest element like we did for every other element from a1 to an minus 1. We cannot do for this element. But here in this question, the constraints allow us to do n square. So what we can do is brute force for this. For just let's I equal to 1 to n minus 1, n minus 2 actually. And for j equal to I plus 1 to n minus 2, we can just take maximum of current comma an modulo ai plus aj. And this n square for loop will give us the maximum answer we can get from an. So our final answer would be maximum of a1, a2 till an minus 2, then an minus 1, and then this. Whatever we get the maximum value from this. Let's just name it curve. And this would be our final maximum answer. So we know all these in O of 1. And for this, we can just do a loop of O of n square, just basically brute forcing the AI and AJ values, and we'll get our answer. So overall, our answer would be O of n square, since this is O of 1 square and O of 1 rest is O of 1. So overall, it will be O of n square. I'll show you guys the code. Basically, we take input vi and then we sort it. And obviously, if I have already sorted the array, I know that a1, a2 till an minus 2 are less than an minus 1. So I don't need to consider these. I can just take max of an minus 1 and curve. That would also give me the answer, since an minus 1 is already greater than these. So I just initialize my answer with n minus 2. It is in my solution, it's 0 based. So this, and then I can just run these two for loops to calculate the maximum answer for n minus 1, which is the largest element. So I calculate the maximum answer and then I see out the answer. So the overall time complexity would be n square. Did you guys get this solution? If okay, so let's move on to the next question. Problem D. So the difference between the two versions is the definition of good. Okay, that is just, let's leave that. An array A of size n, where n is even, is said to be good if it is possible to choose a continuous cyclic subarray of size n by 2. Okay, and then multiply all the elements in this subarray by -1 to make the total sum of the array less than 0. Okay. For example, this is good because we can choose the subarray 2 and multiply it by -1 to get 1 minus 2, which has the sum of -1. However, this is not good. Further, this is good because you can choose the cyclic subarray contain both 4s. Okay. And change the array to -4, 1, 1, -4. You are given an integer array n and a binary matrix M of size n into n and want to count the number of arrays A of size n that satisfies the following conditions. 1 less than equal to AI less than n and M of AI is 1, then A is good. Okay, since the answer may be large, output it modulo 10 to the power 9 plus 7. Let me explain the question. Basically, first in the question, we have the definition of a good array. So let's understand what is a good array. Any given array A would be a good array if I can choose a cyclic subarray of size n by 2. What is a cyclic subarray? I can either choose, let's say this array A has size n. So it is a good array if I choose a cyclic subarray of size n by 2 and multiply all the elements by -1 and Then I take the sum of the array. And now if the sum of the array is negative, strictly negative, then the array is said to be good. Basic, and we can also see it like this. Basically, let's let the sum of this subarray as A and rest of the elements as B. Then B minus A should be less than 0. Since the new sum would be sum of all these elements plus, since the total sum would be sum of all these elements plus sum of all these elements, and since we multiplied these elements by -1, the total sum would become B minus A, which has to be negative for this to be a good array. And for choosing the cyclic subarray, we can choose it like this, or maybe we can choose some elements from here and then some elements from here. Let's say some I elements from here, or n by 2 minus I elements from here. So both of these are a valid form of choosing the n by 2 size subarray. We can multiply now these elements with -1, and if the sum now becomes negative, then the array is good array. So we are now also given a binary matrix M and count the number of arrays A such that M of IAI is 1. So basically, we need to count array A such that A is a good array, A is good, and M of IAI is 1 and AI is 1 to n. So AI elements need to be from 1 to n, and the ith row, AIth and the AIth element in the ith row of M matrix would be 1. I'll explain this through an example. Let's just take the third test case. No, actually the fourth test case. So the fourth test case is 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0. So basically, we need to find array A, right? And array A has size n, which is 4. So we need to follow these properties. So for the first element, we know that A1 must be from 1 to 4. Now what else? This as well. So we know that M of 1 comma A1 should be 1. So M of 1 comma A1 should be 1. And since this is the first row, second row, third row, fourth row. So M comma 1 of A1 should be 1. So A1 can only be 4. 1, 2, 3, 4. Let's just write it like this. So A1 can only be 4. Every other element is 0 in this row. So A1 has to be 4. Then for A2, we have two choices. It can either be 1 or it can be 4. So either 1 or 4. For A3, again, we have two choices, either 1 or 3. For A4, again, there is only one choice. It can only be 3. So like there can be several arrays made from this matrix. It can be 4, 1, 1, or 1, 3, or 4, 1, or 4, 3. These all arrays are possible. And now we need to calculate how many good arrays are in this. So first array, we can see that if we just -1 here and -1 here, then it would become -7, and -7 plus 2 is -5. So this is a good array. Second, again, we can just take the last two, and again, it will be a good array. Same, we can take the last two, it would be good array. Now, if we take the last three, then the sum becomes 0. But still, we can take these two. So taking these two would be 8. So -8 plus 6 would be -2, and then again it is good array. So answer for this test case would be 4. Let's solve another test case. Let's solve the first test case. First test case is 1, 1, 1, 1. So A has two elements. The first element can be 1 or it can be 2. Again, this let me write these. What the hell? So the first element can be 1 and it can be 2. Second element again can be 1 or can be 2. So the arrays that can be made out of this would be 1 1 1 2 2 1 2 2. So this array, we can see that even if we choose any one of these, the overall sum would be 0. So not a good array. In this we can select 2, then the overall sum would be -1, good array. In this we can select 2, then the overall sum would be -1, good array. Again here, if we select 2, the overall sum would become 0. So not a good array. So these two are good array and answer would be 2. That was for the question. Let's see the constraints. Constraints you have given n less than equal to 100 and sum of n square over all test cases does not exceed 10 to the power 4. So we can at max run n to the power 4 because that would be of 10 to the power 8. This is the maximum we can run. Let's see how we can solve this question. Let's say that I have an array A. Let's first find out some good way of finding whether the array is a good array or not. So let's say we are given some array A and we need to check if it is a good array or not. 1 2 3 4 till n. So let's say I've chosen some random subarray from this array A. Let's just randomly select this subarray and let its sum be A. So this must have n by 2 elements. And the other elements, let's just denote it sum by B. So if we choose this subarray, then our sum after multiplying these elements with -1 would become B minus A, which if it is negative, then the array is good. Then it is a good array, right? But let's say that it is positive. Then what happens? Basically, if B minus A is positive, then what we can do, we know that A minus B would be then negative. If this, then we know that this, since if we multiply minus on both sides of the inequality flips, or we can just take A to this side and B to this side and we'll get this inequality. So we know that A minus B is less than 0. And if A minus B is less than 0, what I could have done is I could have chosen this subarray with since this had n by 2 elements, this would also have n by 2 elements. So I could have chosen this subarray and multiplied all of its element by -1, and then A minus B would have become 0. A minus B would have been the new sum and that would have been 0. So even if the B minus A is positive, again the array is good. That is a very important discovery, that if we have some array which has some negative or some positive, then we can make the good array. We can say that the array is good. So every subarray of n by 2 size must have its subarray sum as B minus A should be equal to 0. B should be equal to A. So that means every subarray of n by 2 size must have sum of total sum by 2. If that makes sense, total sum by 2, because only then this A would be equal to B. If A is total sum by 2, only then A would be equal to B, because A plus B is total sum. And since we are saying A is equal to B, then that must mean that A equal to B equal to total sum by 2. And if A and B are not equal, then one of these conditions would be true, and that would mean that the array is good. So A and B must be equal for the array to not be good. So every subarray of n by 2 size must have sum of total sum by 2. Or in other words, must have the same sum. Must have the same sum. So I feel that checking this condition would be far easier than checking that condition. Checking for these conditions would be quite difficult as compared, since this is pretty straightforward. Every subarray must have the same sum. So let's analyze this idea. Let's say we are given an array A, and let's say we have chosen some subarray as this. It has n by 2 elements. So there must be some element before it, and there must be some element after it, right? And there must be some elements here on the end. Let's call this A1. No, not A1 actually. AI, AJ, AK. So since all the subarrays of n by 2 size must have the same sum, right? Since all should have same sum. So if I am saying that this subarray has sum A, then this subarray must also have sum A. Actually, this subarray, I am just removing this element from the last subarray and inserting this element. I am shifting this by 1, shifting this to the right by 1. So this subarray must also have some A for A to be not good. For the array A to be not good, both of these subarrays should have the same sum. So let's denote some of this as B for now. So B would be AJ plus A. Basically, we had A originally and then we added AJ and subtracted. Oh, wait, let me rename this as AK. This would be AI, AJ, and AK. Sorry, my bad. So basically, we are adding this element AK and we are subtracting this element AJ. Right. And the new subarray we are getting is B. And the old one was A. And since for A to be not good, capital A to be not good, B must be equal to A. Since these two subarray have to have the same sum, right? So B should be equal to A. And if we take B equal to A, this equation gets solved to AK is equal to AJ. And we also know one thing, that this had size n by 2. So there must be n by 2 minus 1 elements in front of AJ in this subarray. And then the next element was this. So K must be equal to J plus n by 2. So what we can further simplify this equation as AJ must be equal to AJ plus n by 2. This. Now, if this condition is true for every J, if this condition is true for every J, what that means is basically, let's say I had this subarray for some J, and if this element and this element are equal, then this subarray would be equal to this subarray. And now again, if this element is equal to this element, so now this subarray would be equal to this subarray. And similarly, we can keep going forward. We will get the next subarray as this. And now all of these three subarrays would have the same sum if this property follows. Basically, if the green ones had the same value and blue ones had the same value and purple ones had the same value. So this is the property that if followed for every J, then the array A is not good. So what we can do now is calculate the total and then subtract the not good arrays from it, and then we'll get the good arrays. So basically now we have another problem. We have simplified the problem to this: total minus the good arrays, not good arrays. So we are currently having two problems. First we need to calculate the total arrays that can be formed, and second we need to calculate the total non-good arrays. And we'll use this property to find the total non-good arrays. For now, let's first calculate the total arrays. So let's say we have some matrix like 1 0 0 1 0 1 1 1 0 0 1 0 1 0 1 1 0 1 3 4 5 6 elements, right? So just randomly put values of the oh. So let's say this is an array and we need to find all of the A's that can be found from this binary M. So we know that A1 would have three choices. Basically 1, 2, 3, 4, 5, 6. So A1 would have three choices. 1, 4, 6. A2 would have three choices again. 1, 2, 5. A3 then has four choices. 1, 3, 4, 6. A4 then has 1, 2, 3 choices. 1, 2, 5. A5 again has three choices. 1, 3, 5, and A6 has two choices. 3, 5. So when I am forming an A, I need to pick one of these three, one of these three, one of these four, one of these three, one of these three, and one of these two. And that would give me a new array A. So basically I can say that total number of arrays A, total number of A's possible would be just 3 into 3 into 4 into 3 into 3 into 2. Basically, first element can be three different, and the second element also has three different choices. Third element also has four different choices. So I can pick any one of these choices and I can just multiply. So these would be the total number of A's. So generalizing it for any matrix I would be total is equal to multiplication of number of ones in each row. So this would just give us the total number of A possible. So that was for the total part. This part we have done. Now we need to figure out how to find this part. So we found out this property that if Aj equal to Aj plus n by 2 over all j, then the array is good. Not good. Sorry, not good. So we can again apply similar idea to what we used to find the number of A's. We just found out the total number of possible choices for each AI, and then we multiplied all of those together. So again, we can here now find total number of different choices for each AJ. How we can find that? Let's say some A3 had 1, 4, 5, 6, 9. These many choices, 1, 2, 3, 4, 5 choices, right? And let's say A3 plus n was in this case, assume 10. So 3 plus n by 2, which is 10 by 2, which is A of 8. let's say this had 1, 5, 3, 9, 7. 1, 2, 3, 4, 5 choices. 5 choices. So for the array to be not good, I need A3 is equal to A8, right? So I need to select the values such that these are equal. So if I select 1 here, I'll need to select 1 here. If I cannot select 4 here because 4 is not possible, I can select 5 here and I'll need to also select 5 here. Or 6 again, I cannot select since 6 is not here. 9 again, I can select and this. So basically, I have 3 choices. I can either give A3, A8 the value of 1 or 5 or 9. I have to give one of these values. I have 3 choices. So basically, again, what I can do, I can calculate the choices for these pairs A1, A1 plus n by 2, A2, A2 plus n by 2, till AN by 2 and AN. So I can find out the choices that I can make for these elements. Let's say it be C1, C2 till Cn by 2. And I can just multiply them. So this would again give me the number of not good arrays. Just like how I calculated the total number of arrays, now this would be the number of not good arrays. If there is some pair AJ and AJ plus n by 2, which do not have a overlapping number, like they cannot be the same number. Let's say if this didn't have these 3 choices, it can only be 4 or 6. So now we cannot make A3 and A8 same. So there are 0 choices that we can make. So the answer would automatically become 0, since if one of these becomes 0, then it would all become 0. So this will be the number of not good arrays. And the final answer would be total minus this. So this was it. I'll show you guys the solution, the code now. Okay, I actually used a slightly different method to calculate the number of not good arrays. It basically does this thing. But what I'm doing is I've made a DP which has the state I comma elements. I comma element. So element is nothing. I don't. Okay. So basically, this would be the sum of all the positions you can say where I and I plus n by 2 are same. So if AI and AI plus n by 2 have a same value, then I can just add dp of I minus 1, I plus 1 actually most. I plus 1, yep, and elements minus 1. So basically, wait, I'll explain this from the code more. That would be more easy. So basically for I comma elements, what I have done is I have iterated over J and found if AR array had the same value at I and I plus n by 2. If I and I plus n by 2 both can have the value J, then what I have done is I have added dp of I plus 1 into elements minus 1. So since this is the same, I am adding the same thing over and over again. What I could have done is answer plus equal to choice into dp of I minus I plus 1 comma elements minus 1. So this would be the same as this for loop. Since in this for loop, I am just finding out how many positions I and I plus n by 2 can have the same number j, and I am adding the same value. So if choice is the number of j's which I and I plus n by 2 both can have, which ai and ai plus n by 2 can be. If choice is the number of j's, then this would be the same. This would be same as this, since I'm again and again just adding this same value. So this is the same as this whole for loop. And if we simplify this a little bit, we'll see that answer is exactly this. So how can we simplify this answer? Let's just denote this as choice of I. Choice of I. And then again, this would become choice of I plus 1. And then again, we'll have dp of I plus 2 comma elements minus 1. Minus 2 it would have been that till that time. So we'll just form this chain and we'll get the final answer as C1 into C2 into C3 till Cn by 2. I just did it this way because I don't know, I did it just in the contest it happened. So that's how I did it. And let me show you the other code. This was just taking the input array. I take the input string, and for j0 to n, if the string had 1, then I can just put arrij as 1, or I can put arrij as 0. And ct is basically the number of ones in each row. This, since total was a multiplication of number of ones in each row, I have calculated ct as number of ones in each row and then multiplied total by ct. And since we need to apply mod, we can do this. And total minus dp of 0 comma n by 2 will give me the number of not good arrays. So total minus not good arrays would just give me the answer. So this was the code. You guys can ask if you guys have any doubts. Okay, so I'll now discuss the problem E. So the problem says it is similar to the last problem, but here the subarray that we can choose should not be of size n by 2. Can't be a cyclic subarray. It has to be a continuous subarray of size n by 2. So basically an array A of size n where n is even is said to be good if it is possible to choose a continuous subarray of size n by 2 and then multiply all the elements in subarray by -1 to make the total sum of the array less than 0. For example, this is good because we can choose the subarray 2 and multiply it by -1 to get 1 comma -2, which has the sum of -1. However, 1 comma 1 is not good because the sum would be 0 at max, at minimum. And further, 4114 is also not good because you're not allowed to choose a cyclic subarray. The expected time complexity would again be just like the last question. It would be O of n to the power 4. So that was it. I'll explain you guys problem. Same as last problem. But now we cannot take cyclic subarray. So now what we need to see, like, what does this new additional property change in our previous solution? What changes does this make now? Basically, we found out in the previous solution that each subarray should have the sum equal to total sum by 2. If it was not equal, then we'll always have a way to make the given array good. To prove that the given array is good, we'll always have a way. So cyclic subarray, we cannot take cyclic subarrays now. So what will happen is, now we only need to check for these arrays: this, 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 and so on. Until here, we cannot take cyclic subarrays. Back then when we were taking, so now let's say if I choose this subarray, and this subarray has some A, let's say, and rest of the elements have some B. So if I choose this subarray and multiply all its elements by -1, my total sum would become B minus A, which let's say is positive. So during our last question, what we did was basically chosen this subarray and multiplied -1 to its elements, and now the sum becomes A minus B, which is negative. So even if this was positive, then the array was good. But now, since we are not allowed to take these subarrays in, we are not allowed to consider these subarrays. So now we cannot say, if this is positive, we cannot say that the array is good, since we are not allowed to choose this. So that will change our answer in some cases. So basically, we still have one overlapping case from the last question, which would be, we have these elements 1, 2, 3, n by 2, and n by 2 plus 1 till n. So let's say that the overlapping thing from last question is this case, where we can choose these two subarrays. Let's say if the subarray sum of this was A and subarray sum of this was B. So if we multiply all elements of A by -1 and take the total sum, it would be B minus A. And if this is positive, then we can choose this as our subarray, and then the sum would become A minus B, which will be negative. So this array will be good. So again, if we try focusing on calculating the number of not good arrays, then for a not good array, sum of this must be equal to sum of this, right? Because only if sum of this is equal to sum of this, then A equal to B, and then only A minus B would be equal to 0, because it cannot be positive or negative. Then we can make the array good. So first n by 2 elements must have their sum equal to last n by 2 elements. So let's denote the sum of the first n by 2 elements by S. Let's denote sum of these by S. So S would be the total sum by 2. Since the total sum was equal to A plus B, total sum was A plus B, and A and B both are equal to S, so 2S. So S is equal to total sum by 2, right? So if A is not equal to B, then the array is immediately good. So if to calculate the number of not good arrays, we just need to focus on the arrays where the sum of first n by 2 elements is equal to the sum of last n by 2 elements, right? So let's make this our goal for now. We need to find the subarray of length n by 2 with sum greater than S. basically if we have an array 1, 2, 3 till n, and the sum of first n by 2 elements is equal to the sum of last n by 2 elements, right? And this is equal to s. So if we find a subarray of n by 2 elements with sum greater than s, then since the total sum was 2s, total sum was equal to 2s, and we found a subarray of n by 2 elements which has sum more than s. So if we multiply all these elements by -1, we'll have some leftover sum, which let's denote by b a, and the total sum will become a minus this, let's say b, a minus b, and we know that a plus b is 2s. So a is 2s minus b, and since b is greater than s, then a would be less than s. So a would be less than b, and so a minus b would be negative, right? So if I find a subarray that has sum greater than s, then this array is not good. Even after having the first n by 2 elements and last n by 2 elements with sum s, this subarray would not be good. So let's generalize this a little bit. So I am basically saying that ai plus 1 till ai plus n by 2 minus 1. So subarray sum, if this is greater than s, then the array is not good. So we can rewrite this like this: a1 plus a2 till we can do ai plus n by 2 minus 1. And since we previously did not have elements before ai, we can subtract them. So subtract a1, a2 till ai minus 1. And if this is greater than s, then the array is not good. Also, we know that s is equal to a1 plus a2 till an by 2. So we can put the value of s here. We are trying to eliminate s from this equation so that we can solve this question in a general manner. So we'll put s here, and then we will get s plus a n by 2 plus 1, a n by 2 plus 2 till a n by 2 plus I minus 1, and subtract a1, a2 till ai minus 1. And this is greater than s. So if we if we find some subarray which has sum greater than s, then it will become good, since we have now a minus b less than 0. So this would be condition for making an array good. So this is the condition for making some array good. And for it being bad, what we can do is, just a second, let's first subtract s from both sides. And then this will become n by 2 plus I minus 1 minus of a1 plus a2 till ai minus 1. This greater than 0. Now this is the condition for the array being good. To make the array bad, this would be a n by 2 plus 1, comma a n by 2 plus 2 till a n by 2 plus I minus 1 minus a1 plus a2 till ai minus 1 should be less than equal to 0 for an array to be bad array, not good. So since we took a general starting point I, we need to make sure this is true for all the subarrays. For all the subarrays. And since we generalize the subarray to be ai to ai plus n by 2 minus 1, we need to have I from 1 to n by 2. So we need to calculate how many arrays have this condition, satisfy this condition from I equal to 1 to n by 2. And that would be the number of bad arrays. So we can use DP to solve this kind of problem. Let me define the state and then I'll explain you guys. Let the DP state be DP of IX. This is number of ways to choose the elements A1, A2 till AI and the corresponding elements an by 2 plus I and an by 2 plus 1, an by 2 plus 2. So this denotes the number of ways to choose the elements these such that this let's just give it some variable a1 plus a2 till ai minus an by 2 plus 1, an by 2 plus 2 till an by 2 plus I. So this TP will give us the number of ways such that this minus this is equal to x and the value of the previous states. What I mean by previous states is that the value from a1 to ai minus 1 and here from an by 2 plus 1 till an by 2 plus I minus 1. So difference of these also should be positive and we can go backwards from here and all those should be positive because this should be true for any ai. So value of all the previous states should not fall below 0. So this would be our state and then our total number of bad arrays would be dp of 0 comma wait, first let me show you guys the transitions. The transition for a state dp of I comma x. So where can this state come from? It must come from some dp of I minus 1, basically this and this. It must come from this state. So what can be the transitions? We can just iterate over all possible values of ai and an plus n by 2 plus I and we can transition from there. So basically dp of I minus 1 and x minus d. We can come from this state to this state where d is the value of ai minus an by 2 minus I. So d is ai minus an by 2 minus I. So we can just sum of all these states, we can add this into dp of I comma x. Since upon coming to dp of I comma x, we could have come from these states only. Let's analyze the time complexity for this dp. So number of states are, since I can be from 1 to n, and x is actually sum of these minus sum of these. So sum of these can be till n square. Since a1, a2, ai can all go to n. So maximum sum would be till n square. So number of states are n cube, and total number of transitions. In total number of transitions, we are looping over all the possible values of ai and all the possible values of an by 2 minus I. And that also can be again n and n. So transitions can also be maximum n square. So overall time complexity of this would be O of n to the power 5, which is not allowed in this question as we saw it. We can only do up to O of n to the power 4. So we can do one thing to optimize this. Since I noticed that ai minus a n by 2 minus I, these are n total n square different options, but they all are from minus n to n only. Since the value of ai can only be between between 1 to n, and value of this can only be between 1 to n. So when we subtract these, it can only be between minus n to n. So what I can do is I can store the count. Basically, I can store CT ID as the number of pairs of values of ai and an by 2 minus I, as the number of pairs of these values where ai minus an by 2 minus I is equal to d. So we can just count these number of these pairs as d. So now we know for all how many pairs would give me the value d. So now we don't need to explicitly calculate this for all the pairs. What we can do is, instead we can iterate from minus n to n and just sum it like this. Sum of dp I minus 1 comma current x minus d into how many ways we can get the sum d. And since d is only from minus n to n, now our transitions would be O of 2n. And the total time complexity would now become O of n cubes, which was the state, and n. So O of n to the power 4. So we have reduced our time complexity from n to the power 5 to n to the power 4. And now we need to calculate this. And calculating this is quite simple. What we can do is just for loop over j is from 1 to n, and again for k 1 to n, if ai can take value j and ai plus n by 2 can take value j, then I can just simply count of I and whatever is the difference between these two plus plus. So that way I'll get the count of all, and I won't have to do I would not have to do this n square transition inside the DP. I can pre-calculate for each difference. And once I pre-calculate for each difference, I can calculate the DP like this. Then I can solve this DP in O of n to the power 4, and my total number of total number of not good would be given by dp of n by 2 comma 0. Since I need all possible i's tail n, I need to check for all possible i's tail n by 2. So this would give me all the not good arrays. and I can subtract from the total. I'll show you guys the code for this question. So basically, also since current state only depends on the last state, since dp of I is only depending on the last state x minus d, what we can do is we can use previous dp and new dp to space optimize this. And now then we won't have to actually allocate n to the power 3 space. And we can just allocate n square space for I minus 1th state, and from that we'll calculate the ith state, and from the ith state we'll calculate I plus 1th state. I'll show guys the code. I take the input x, and now what we have here is we just initialize n square dp, which would be the 0th state for now, and new dp would be filled by this. And what is waves? Waves is basically what CT was here. CT is waves. So if AI can take the value x and AI plus n by 2 can take the value y, then I just do waves of x minus y. This plus n is just an offset. Basically, since I don't want values from minus n to n, I'll just make them 0 to 2n. It's just an offset type of thing. So I'll just plus ways. Now these two we have initialized the CT variable, and for the new DP, what we can do is new DP of j plus d is new DP of is old DP of j, which basically means I minus 1 comma j. From here we can go to I comma j plus d into count of I comma d ways. Ways basically plus equal to. So this is our transition, just like I explained. So this transition, and we just do mod and dp equal to ndp, so that I'll use less memory. And this is the total number of ways. I just count the number of ones in each row and multiply, and total minus of dp0, which would be dp of n by 2 comma 0, because it is the latest and because it is the last iteration of the dp, so it would be n by 2, and total would be the answer now. So that was it for the discussion. If you guys have any doubts, you can ask. So okay, I think I'll end the meeting now.